Hello students, in this video we'll be talking about reaction mechanisms in general and especially talking about reaction mechanisms in the context of complex that is multi-step reactions and how they can be used to deduce order of a complex reaction and vice versa. So the first subtopic that we are doing under this uh, topic is energy profiles of elementary and complex reactions. How do they differ from each other? So I'll ask you to just pause the video here and make your initial observations as to what fundamental differences do you see between the energy profile diagram of an elementary reaction versus that of a complex reaction. When you have made your observations, you can continue the video. All right. I believe the first observation that you have made here is that elementary reaction, as the name itself suggests, happens in a single step. So in that single step, the reactant change to products via the formation of a transition state, all right, which is a very unstable entity and cannot be isolated in a reaction. Whereas when we observe the potential energy diagram, energy profile diagram of a complex reaction, what we see here is that again there are multiple steps, and those multiple steps create multiple transition states. And between two transition states, we have another entity that is created, which is called as an intermediate. So the first question that you may have is, what is the difference between a transition state and an intermediate? In our previous discussions, we talked about transition states being entities which have partial bonds being formed, and those entities actually cannot be physically isolated. In contrast, reaction intermediates involve species such as free radicals, that is, atoms having odd number of electrons or molecules. Such entities are unstable and they last very briefly, but they can be isolated in a reaction. Another example of an intermediate is carbocation, which we will talk about in detail under organic chemistry. But the underlying idea is that intermediates are created during the course of a complex reaction, that is, during the course of a multi-step reaction. They are not the final product, but they are generated, and unlike transition state, they can be isolated because they are relatively more stable. So let's have a look at the energy profile diagrams of some elementary reaction followed by a complex reaction. So this is a fairly simple example of an exothermic elementary reaction, because you can see that the enthalpy change here between the reactant and the product, the enthalpy change is negative, and you have the formation of a single transition state here. Notice that the a more appropriate label for the x-axis would be reaction coordinate, although that is synonymous with the progress of the reaction, and that for the y-axis is actually potential energy. So here is another example of the energy profile diagram of an elementary reaction where hydrogen molecule is combining with iodine molecule, okay, to make two molecules of hydrogen iodide. Now, unlike the previous example, this one here is an endothermic reaction, which you can make out by looking at the final enthalpy change between the reactants and the products. And this is also an elementary reaction because it just passes through one transition state, which you can see is again a entity with partial bonds, which is highly unstable. Now, this here is the energy profile diagram of the complex reaction, which is represented as two ozone molecules make three oxygen molecules. Now, this might look at first glance as a simple reaction, but we can see that this reaction is actually made up of two steps. So if we relate these steps with the energy profile diagram, we can see that when we start with the reactant, which is an ozone molecule, so this ozone molecule forms a transition state which would have partial bonds formed and leads to formation of an intermediate. Now, O2 here cannot be considered as an intermediate because it's one of the final products. But the other entity that is created is an oxygen with an odd electron. That's a free radical. So that is being created here. And then this oxygen free radical reacts with another ozone molecule to create the final product, which is two oxygen. So remember, three oxygens, out of the three oxygens, one oxygen was actually created in the first step itself, and the other two oxygen molecules were created in the second step. So again, how is this different from an elementary reaction? In an elementary reaction, there was a single transition state, there was no intermediate. However, here in a complex reaction, you have multiple transition states and you have an intermediate. Please understand that intermediate is relatively more stable than a transition state, as you can probably guess by looking at the potential energy, but it is not the final product. So it does not appear in the overall chemical equation. So let's now understand about rate determining step in a complex reaction. So here is the energy profile diagram for a hypothetical reaction. This is the hypothetical reaction here. A plus B plus C gives T plus X. So here A, B and C are our reactants and T and X are our products. I would like you to pause the video in case you find the information quite overwhelming, and when you have comprehended the diagram itself and the reactants and products with respect to the diagram, you can continue the video. All right. So again, in the energy profile diagram, we see that it is a complex reaction because there are two transition states being created and there is an intermediate formed as well. The second observation that we can make is that it is an exothermic reaction because the overall enthalpy change is negative. So let's see what's happening in the two steps. So in the first step, only A and B. Okay, so out of the three reactants, the first step is only involving two of them, which is A and B. So A and B are combining to form an intermediate, which is Y. Okay, so C is not the intermediate here. C is the third reactant which will come into play in the second step. But in the first step, it's just A and B forming the intermediate Y via passing through the first transition state. So we'll call this transition state TS1. Now once this intermediate Y is formed, it combines with our third reactant, which is C, to make another transition state. Let's call this TS2, and eventually create the final product, which is T and X. Now, if you see the overall mechanism of this reaction, if you add them together, you see that the Y actually cancels out from both the sides. And so, if you add all the steps of the mechanism together, they should be stoichiometrically consistent with the overall reaction that we were beginning with. All right. So again, in this multiple step reaction, You are starting with reactants A and B, which first formed the transition state 1, formed an intermediate which is Y. This Y combined with the third reactant again passed through the second transition state and formed the product. So I hope that by now you are pretty clear as to how is a complex reaction different from an elementary reaction. So, if we are now clear about the various steps which were involved in this complex reaction, let's now try to identify what's a rate determining step. So, in a complex reaction, not all steps proceed with the same pace. Some steps are relatively slow and some are relatively fast. So the slowest step in a complex reaction is called as the rate determining step. Now, when we say it's slow, it's not just slow by a very small amount. Usually, the difference in speed is order of magnitudes of thousands or maybe even more. Okay, so the slowest step in a multiple step reaction is usually called as the rate determining step, and it is slow because it requires the highest activation energy. So again, going back to the previous example, here you had the first transition state and this was the activation energy. Let's call this EA1, which formed the first transition state, which was TS1. And in the second step of the reaction, the intermediate Y reacted with our third reactant C, formed transition state 2, and made the product. So, by looking at the magnitude of activation energy EA1 and EA2, can you determine which of the two steps, the first one or the second one, is the rate determining step? I'd like you to think and pause the video and then continue when you have an answer in your mind. All right. So if you guess that the first step is the rate determining step, you are absolutely right. That's because this has a considerably higher activation energy than the second step. And as a result, this is a much slower step compared to the second step. So this is the rate determining step of this particular reaction. So, how is order of a reaction related to all of this basically? So, by now, using the specific context of this hypothetical reaction, we have deduced number one, it's a complex reaction which is consisting of two steps forming transition state 1 and transition state 2 and having an intermediate which is Y. The second thing that we have so far determined is that the first step is the slower of the two steps. That's because it has a relatively higher activation energy. So, how does this lead us to determining the order of a reaction? Basically, since the first step is the rate determining step here, only the reactants involved in this rate determining step will contribute to the order of the reaction. In a sense, the molecularity or the colliding molecules in the rate determining step constitute the order of the reaction and hence appearing in the rate equation. So in this specific hypothetical reaction, it's only the reactants A and B which are involved in the rate determining step. And since there is only one molecule of A and one molecule of B involved, therefore the molecularity is 2 of this elementary step. So when we write the rate law, we say that the order of the reaction with respect to A is 1 simply because there is only one of A involved in the rate determining step. Similarly, The order with respect to B is also 1 since there is only one of reactant entity B involved. But the order with respect to C is 0. That's because C is not part of the rate determining step. So essentially, this one is a second order reaction, and this particular reaction, the rate, doesn't really depend on the concentration of C. This is the reason why rate of a reaction might depend on the concentration of some reactants but not depend on the concentration of other reactants. And the reason is quite simple. The reactants which are involved in the RDS are the ones that will determine the overall rate of the reaction and hence contribute to the order of the reaction. Whereas the reactants that are not part of the rate determining step will not contribute to the overall rate of the reaction and hence do not appear in the overall rate equation. If some of the information is not clear to you, you can pause and maybe just rewatch this entire section, and if it's still not clear, please reach out to me in person for further clarification. So the previous example we saw was a fairly simple one, and that's because the first step itself was the rate determining step. But what if in a multiple step reaction the first step is not the rate determining step and you have an intermediate involved? So let's see one example here. So we have a reaction, um, again A plus B plus C giving you D. So this energy profile diagram is very different from the previous one, and that's because you can see here that unlike the previous energy profile diagram, the activation energy of the first step is considerably smaller compared to the activation energy of the second step. Let me just put a few labels so that it's clear what's going on in this reaction. So this is transition state 1, that's transition state 2, and the Z here is our intermediate. Okay, so by again comparing the activation energy of step number 1, which is basically A plus B gives Z, and step number 2, which is Z plus C gives D. If we compare the activation energy of these two steps, the conclusion is that the second step is actually the slower step because the activation energy for the second step is much higher. So now if we see, that means the rate of the reaction is only going to depend on the concentration of entities involved in the slower step. But this is quite perplexing because Z is not a reactant. Z is an intermediate and hence cannot appear in the rate equation because rate equation is always written in the context of reactants. So how do we overcome this problem? Let's first of all write the rate equation in the way it just makes sense to us in the context of the RDS. So with the context of the RDS, rate equals K, since the coefficient of Z is 1. So with respect to Z, the order is 1. And with respect to C, the order is 1 as well. But as we know, Z cannot appear in the overall rate equation, that being an intermediate. But we know that a Z, a single entity of Z, was in turn made from one entity of B and one entity of A. So instead of having molar concentration of Z raised to the power of 1, we can instead substitute it with the things that led to the formation. So this in turn becomes molar concentration of A raised to the power 1, B raised to the power 1, and C raised to the power 1, which remains unchanged from the above step. So essentially what we are doing is that we are replacing the intermediate with the things that were involved in that formation of the intermediate. So here, instead of writing Z, we wrote molar concentration of A raised to the power 1 and B raised to the power 1, simply because in the formation of one entity of Z, we had one entity of A and one entity of B. See, the overall order of the reaction is 3, and this becomes the rate equation. So in a sense, if you have a, a later step as a rate determining step, you need to consider the things that led to the formation of intermediate, the reactants that led to the formation of the intermediate, and then include those reactants in the final rate equation. Again, if you find this information or part of the information confusing, I recommend you to re-watch this section again. And if you still require any clarifications, please reach out to me in person. So I'd like you to pause the video again. This particular slide refers to the summary of the information that we have covered in the previous slides. Um, so just pause it instead of me reading it out. I think it would be better if you can just read it out. You do not need to take notes if you think you are already familiar with them. But if there is something that perhaps you didn't note earlier, you may just note it down here. All right. So now we come to the second part of this tutorial as to how to deduce possible mechanisms if a rate equation is given and vice versa, meaning if a mechanism is given, how do we deduce rate equation from that? So let's just address both these aspects. So instead of going through theory, what we'll do in this particular section is actually we'll be going through some questions themselves and then try to apply our understanding to get the answer and understand the concept itself in the process. So you have an overall reaction 2P plus Q gives R plus S. And this reaction occurs according to the following mechanism. Do understand that when we say mechanisms, all of the mechanisms are proposed mechanisms, and one mechanism may be more acceptable than the other. We'll see the reasons as to why some mechanisms are preferred over others. So here the first step, that is P plus Q gives X, is the slow step, and the faster of the two steps is the second step here. Okay, so the difference between this specific type of question and the one that we saw earlier is that you are not necessarily given or provided with an energy profile diagram. Sometimes you are just given the mechanisms themselves, and you have to make out by looking at the mechanism as to what is the rate determining step, which is quite obvious here, the first one being the slower one, and using that you need to determine the rate equation. Do remember that in the earlier syllabus, rate equation was referred to as rate expression. That's why the term rate expression is used here. So if you have understood what was the correlation between order and rate determining step, I'd like you to pause the video here and continue when you think you know the answer. All right. So we see here that the rate determining step involves one entity of P and one entity of Q. So that means rate should be equal to lowercase k times molar concentration of P raised to the power 1 times molar concentration of Q raised to the power 1. Some of you might think, why is it not P raised to the power 2? Because there are two of the P's involved. Well, that is for the overall reaction, but in the rate determining step, there was only one entity of P and one entity of Q involved. And as I said earlier, the molecularity of the rate determining step is basically what leads us to the order of the reaction. So this is the rate equation, and so the answer here is C. Rate equals lowercase k times molar concentration of P times molar concentration of Q. Because if nothing is written, we assume that the powers are 1. Now, this is another example where rate equation is given and different mechanisms are provided, and you'll have to guess as to which mechanism is consistent with this particular rate equation. Now, we can use the method of elimination here to identify which is the one consistent. Now, in the option A, the first step is the fast step and the RDS is the second step. So you can say that for this particular mechanism, the rate equation becomes initially K times I times B, but we know that intermediates don't appear in the rate equation. So this I was in turn made up of two entities of A. So this becomes K times molar concentration of A raised to the power 2 times B, which is not the one that is being provided. So this particular mechanism is rejected. Let's try with the second one. So in the second one as well, we can see the slower step is the second step. So using this, rate equals lowercase k times I times a, but then I itself was made up of one entity of a and one entity of b. So this in turn becomes a raised to the power 2 because there was already an a present here. So if we bring one more a, that becomes molar concentration of a raised to the power 2 times molar concentration of B, which is again not the same as what we are provided in the question. Let's examine option C now. So in option C, the first step itself is the slowest step. So this should be fairly quick. Rate equals K times molar concentration of A. There is no B here at all. And so this is also not consistent with our rate equation. Okay, now if we use the method of elimination, we can already see that D should be the right answer, but let's also theoretically kind of get our heads around it as to why this is the right answer. So here again, the second step is the slower step. So we write rate equals K times molar concentration of I times molar concentration of A. But I itself was made up of one entity of B. So instead of I, we can write B. This becomes K times molar concentration of A times molar concentration of B, which is exactly what the rate equation is provided in the question. All right. So that's how you identify which mechanism is consistent with the rate equation. So here is another example. So uh, of a question where a a set of mechanism is here, and you have to identify which step of this proposed mechanism is the rate determining step, which kind of follows the rate equation. Okay, so now the first step, clearly the first step cannot be the rate determining step, because if the first step was the rate determining step, you would not see any H2 in the rate equation. But there is H2 in the rate equation. So the first step clearly is not the rate determining step. Now, in the second step, we have N2O2, which is clearly an intermediate because it's not appearing on the reactant or the product side. So, N2O2 is our intermediate here. So, we can see in the second step, the intermediate reacts with H2 and makes N2O and H2O. N2O is another intermediate here because it also is not appearing in the overall rate in the overall reaction. So if second step was the slowest step, and if that was the rate determining step, then the rate would be equal to K times N2O2, which is our intermediate, first intermediate, times H2, right? But since intermediates don't appear in the rate equation, we replace N2O2 with what it was made from. So it was made from two molecules of NO. So we can write it as K times molar concentration of NO raised to the power 2 times H2, which is exactly what the rate equation is. But also let's try to find out why third step cannot be the rate determining step. So in the third step, we have N2O, which is our second intermediate. Let's call this I2, which is reacting with H2 to make N2 and H2O. So if this was the case, then the rate equation would have been rate equals K times molar concentration of N2O times molar concentration of H2. Okay. However, N2O itself was created from N2O2 and H2. So in that case, that would transform to N2O2, and because there is already an H2 here, that would be H2 raised to the power 2. But N2O2 is also an intermediate, so this cannot be the rate equation. So what is N2O2 created from? It's created from 2NO. So this becomes K times NO raised to the power 2 times H2 raised to the power 2, which is clearly not what the rate equation is. So we have proved not only using method of elimination but also by logical deduction as to why the second step had to be the slow step in the overall proposed mechanism. If this explanation is not clear, I would like you to again review the video, review this part of the video, and reach out to me if you have any clarifications. So for the same reaction, there is another proposed mechanism, and I would like you to pause the video here again and try to see using reasoning that is this mechanism also consistent with the rate equation. Just to make it clear, this NO is also this 2 is in the superscript. All right. Okay. So now let's try to see if if this mechanism is also an acceptable mechanism for the above reaction. So here the second step is a slower step. So that means the rate equals K times molar concentration of N times molar concentration of NO, right? But N over here is an intermediate because it's not appearing on the reactant or the product side. Remember, the product side is N2, which is a nitrogen molecule. It's not a nitrogen atom. So the nitrogen atom here is an intermediate. So that intermediate was itself created from one entity of H2 and one entity of NO. So instead of writing this, we have K times H2, and since there was one NO already present, so this becomes NO raised to the power 2. So this mechanism is also consistent as far as the rate equation is concerned. But which of the two mechanisms that we have seen before, the one before or this one, do you think is a more likely mechanism? I'd like you to think for a minute. Pause the video when you're thinking, and then continue when you think you have an answer. All right. So with respect to the intermediates created, N nitrogen atom is something which is very unstable. You know that nitrogen in nature doesn't exist as a single atom. It exists as a molecule, that too with a triple bond here. Okay, so as far as possibility is and likelihood is considered, the other mechanism where N2O2 is a well recorded intermediate is a more stable mechanism with a lower potential energy of intermediates and transition states involved. So that's a more likely mechanism only because the intermediate that's created here is less stable than the intermediates that is being created in the prior mechanism. So here is one last question just to kind of summarize our understanding of reaction mechanisms, rate determining step, and how it's related to the overall rate equation. So here you have the overall equation, which is two molecules of NO reacting with one molecule of bromine to make two molecules of NOBr, and this is the suggested mechanism. So you have to identify which of the statements given here are correct. When you think you know the answer, please continue the video. Alright, so we know that the first statement is correct. That's because NOBr2 is indeed an intermediate because it appears in the mechanism, but it's not either a reactant or product. So it is an intermediate. That's correct. The second statement is the second step is the rate determining step, which is also correct. That's because the second step is the slower of the two steps. Now, if the second step is the rate determining step, then the rate equation should be K times molar concentration of NOBr2 times molar concentration of NO. But since NOBr2 is an intermediate, that won't appear in the rate equation. So instead of that, we have one entity of NO and one entity of Br2. So this would be K raised to the power K times molar concentration of Br2 times molar concentration of NO raised to the power 2 because one NO was already here. This is also the case with the third statement. So, from our observations, all the three statements are correct. Hence, the answer is D. So, this concludes our AHL topic of chemical kinetics. I'd like you now to proceed to the elaborate section where you will be doing some textbook and some past paper question to assess your understanding. And do reach out to me if you have any clarifications. Thank you so much.